Hello, we are given a production function. Specifically, this type of production function is called the Cobb-Douglas production function. So given this Cobb-Douglas production function, we will answer a series of questions. The first question says, given that we have this production function, we should find the marginal product of the capital. So in simple form, that means we are looking for the MPK. Marginal product of capital is just simply equal to the change in the total product divided by the change in the amount of capital used. However, since we have the production in a functional form, so that means we simply take the partial derivative of the total product with respect to capital. So this can also be written as partial derivative, since total product is the same thing as Q. So the partial derivative of the quantity function with respect to capital. So taking the partial derivative, that will be equal to, this is the function. To solve this, we are going to apply the basic rule of differentiation or the basic rule of partial derivatives. That is, we focus on the k. So first, we bring the power of k down, which is 0.5. We multiply it with the existing coefficient, which is 2. And next, we go to k, write k again, subtract 1 from the power of k, and then next we have L, and then the power of L, nothing will be done to it. So what we have simply done here is the partial derivative. So we focused on k, bring the power of k down, and subtract 1 from the power of k. So simplifying what we have, 0.5 times 2, that will give us 1. And then we have k raised to power 0.5 minus 1, that's minus 0.5. And then L raised to power 0.25. So simplifying this simply means we have k raised to power minus 0.5 multiplied by L raised to power 0.25. And you can rewrite this as L raised to power 0.25 divided by k raised to power 0.5. So we brought the k down to get rid of the minus in the power. The second question says, what is the marginal product of labor function? So the MPL function. The MPL is similar to the MPK in the sense that we take the change in the total product divided by the change in labor. So because we are looking for the marginal product of labor, we take the change in total product with respect to the change in labor. And as we said, when we're calculating marginal product of capital, we said since the production is in a functional form, we simply take the partial derivative of the total product, which is the same thing as the quantity, with respect to the input, which is labor in this instance. So the MPL will be equal to taking the partial derivative of this quantity function with respect to L. So we focus on L. L has the power of 0.25. So we bring the power of 0.25 down. Multiply it with the existing coefficient, which is 2. And then we have K. K is not an L, raised to power 0.5. And then we have L, raised to power 0.25. Then we subtract 1 from the power. So simplifying, we have 0.25 times 2, that will give us 0.5. And then we have k raised to power 0.5. And that means we are left with L to the power of 0.25 minus 1, that's minus 0.75. So this is the marginal product of labor function, or we can rewrite it as 0.5 k raised to power 0.5 divided by L raised to power 0.75. So here we have our MPK and here we have our NPL. Next question says we should find the average product of labor. The average product of labor equals the total product divided by the amount of labor used. So in this case, the total product is this production function that we have. So we have 2 multiplied by k, which is raised to power 0.5, and then multiplied by L, which is raised to power 0.25, divided by L. So the total product function divided by the labor. So simplifying, we have 2k raised to power 0.5. So these 2L, we write them as 1, and then the power of the first L is 0.25. Since the sign between these two L's is division, applying the rule of indices, that will be 0.25 minus the power of the second L is 1. So we have 0.25 minus 1. So simplifying, we will have equal to 2k to the power of 0.5 multiplied by L raised to power minus 0.75. And this is the average product of labor function. So we've answered question A, question B, question C. The next question, which is question D. Question D says, if capital is fixed at 9, what is the short-run production function? So question D, which is 4, says capital is fixed at 9. The original production function is equal to f of k and L, and that's equal to 2 multiplied by k raised to the power 0.5 multiplied by L raised to the power 0.25. This was the initial production function. So if capital is fixed, which means most likely the firm is in the short run, so it means we are going to treat k as 9 and then L can change. So which means anywhere we see k, we substitute 9 raised to the power 0.5 multiplied by L raised to the power 0.25. Simplifying, the short-run production function will be 2, 9 raised to the power 0.5, that's 3. Then multiply by L raised to the power 0.25. So Q is 2 times 3, that's 6L raised to the power 0.25. And this is the short-run production function when capital is fixed at 9. And this answers the fourth question. The next question says, at capital fixed at 9, which means we are still in the same short run, what is the marginal product of labor? So let's say E, when capital is fixed at 9, what is the marginal product of labor in the short run? So there are two ways we can approach this. The first way is we can approach this using the short run production that we just got, this short run production function. So we can use Q equals 6L raised to the power 0.25, and from here we directly calculate the marginal product of labor. So the marginal product of labor in this instance is equal to the derivative of the quantity function with respect to the level of labor. Here, we're not going to use a partial derivative simply because we don't have any capital in this instance, as the capital is fixed and has been integrated into the coefficient. So the derivative of Q with respect to L will be, we bring the power of L down, which is 0.25, multiply to the existing coefficient, which is 6, write the L back again, subtract 1 from the power of L. So we have 0.25 times 6, that will give us 1.5, and then L, 0.25 minus 1, that's minus 0.75. And this is the marginal product of labor in the short run. The second way that we can use is we go back to the original marginal product of labor function that we got initially, this marginal product of labor that we got initially, and then we simply substitute the value of K, which is 9. So we simply go to this marginal product of labor function and we put in 9 into the equation. So we have MPL equals 0.5 K raised to the power 0.5 divided by L raised to the power 0.75. If you recall, we said this MPL is actually 0.5 K raised to the power 0.5 and then L raised to the power minus 0.75. If we bring this L to the top, it carries a power with a negative sign. So MPL at K equals 9. That will mean that anywhere we see K in this function, we substitute 9 into it. So we have 0.5 multiplied by 9 raised to the power 0.5, then L raised to the power minus 0.75. Simplifying, we have 0.5, 9 raised to the power 0.5 is 3, then L raised to the power minus 0.75. So we have equals 0.5 times 3, that's 1.5, L to the power of minus 0.75. And then you can see that the marginal product of labor when capital equals 9 in the short run is exactly the same thing. So whether you use the first approach of taking the derivative of the short run production function, or you go back to the original marginal product of labor function and substitute in the value of capital just to get your marginal product of labor at that specific capital level. And this answers question E. The next question says, in the short run, is there a problem of diminishing marginal product of labor? So diminishing marginal product of labor means as more and more of a variable input is used against a particular fixed input, we expect the marginal product of the varying inputs to diminish over time. So F, to prove the issue of diminishing, diminishing can only occur if we take the derivative of the marginal product of labor with respect to the labor, and if the function is less than 0, then we have a problem of diminishing marginal product of labor, or we have a problem of diminishing marginal returns. So we know that marginal product of labor when capital, which is the fixed input, is constant, this is the marginal product of labor function. So we need to check through this function by taking the derivative of this marginal product of labor. So which means we have MPL, L, that's the notation that can be used, which is the derivative of the marginal product of labor function with respect to L. It's also the same as saying we are taking the second derivative of the quantity function with respect to L. So when we take the second derivative of the quantity function or the production function with respect to L, it's going to be the same as taking the derivative of the marginal product of labor function with respect to L. The marginal product of labor derivative equals, so from this function, we differentiate this function with respect to L. So we bring the power of L down, which is minus 0.75, multiply to the existing coefficient, which is 1.5, L, subtract 1 from the power. So we have minus 0.75 minus 1. Simplifying, we have equals minus 0.75 multiplied by 1.5. That will give us minus 1.125. Then L minus 0.75 minus 1, that's minus 1.75. As we can see, this result, which is the functional form, is led with a negative. So that means less than 0. Hence, we can say that we have a problem of diminishing marginal product of labor. And this answers the F question. Last G says, in the long run, what type of returns to scale will this firm experience? Returns to scales. There are mainly 3 types of returns to scale. So number 1 is the increasing returns to scale. Number 2 is decreasing returns to scale. And number 3 is constant returns to scale. These are the 3 types of returns to scale that we have. Given the production function at a particular level or at a certain point, the firm may have an increasing returns to scale or a decreasing returns to scale or a constant returns to scale. So to determine which type of returns to scale this particular firm, given this particular production function, is going to experience in the long run, there are 3 ways we can answer this question. The first way is to use the homogeneity approach. This means that we have a particular given production function, which is F is a function of capital and labor. So if we are going to have an increasing returns to scale going through the homogeneity approach, for an increasing returns to scale, that means F of, when we put in a constant value along with the capital and we put in a constant value along with the labor, if it is greater than bringing out the constant value multiplied with the function of capital and labor, if putting in the constant value along with the input is greater than bringing out the constant value multiplied with the production function, then we have an issue of increasing returns to scale. When we have a decreasing returns to scale, if we put in the constant value along with the input, but it is less than bringing out the constant value multiplied with the production function, then we have an issue of decreasing returns to scale. And lastly, for constant returns to scale, if we put in the constant value into the production function along with the input, and the answer or the function it gives us is exactly equal to bringing out the constant value, and we still have the same production function and they are equal, then we have a constant returns to scale situation. Following this approach is quite mathematical and it's quite for advanced economics. So except if you're someone who is studying economics at the master's level, this approach may not be required for you to be able to determine the returns to scale level of a particular firm given a particular production function. If you would like to learn about this approach, you may check the video linked up here, or you may check the description below for how to determine homogeneity of a function. The second way, which is the easiest of the lot, is the doubling approach. This simply means if we have a situation of increasing returns to scale, that means if we double the inputs, the output will more than double. However, if we are to double the inputs and the output less than doubles, that means we have an issue of decreasing returns to scale. But if we double the inputs and the output also doubles, then that means we have a constant returns to scale. What does this mean and how do we apply it? Let's use the production function that we have, which is Q equals F of capital and labor, and that's equal to 2 times capital, which is raised to power 0.5, multiplied by labor, which is raised to power 0.25. Let's say, for example, the level of capital is 2 and the level of labor is 3. So if we put in these values, so that means we have Q is a function of capital, which is 2, and labor, which is 3. So anywhere we see K, we put in 2, and anywhere we see labor, we put in 3. When you input this and solve it using your calculator, you will have quantity equals 3.72 approximately. Now, let's take this input and let's double them. So, previously, K was equal to 2. The double of 2 is 4. And previously, L was equal to 3. When we double the L, that will give us 6. So now, let's take these inputs and put them inside the production function. So we have Q equals F of 4 and 6. So that means anywhere we see K, we put in 4. And anywhere we see L, we put in 6. Punch this into your calculator to simplify. You will get 6.26. So that means when the inputs are doubled, the output, which is 3.72, which is the first output, and the second output is 6.26. 3.72, if we are to double 3.72, so if we say 3.72 multiplied by 2, that will give us 7.44. This is the double output. But when we doubled our input, the output that we got is less than 7.44, which means input doubles, but output less than doubles. So in this situation, we say we have decreasing returns to scale. If our output was exactly equal to 7.44, that would have been a constant returns to scale. If the output was greater than 7.44, that will have been increasing returns to scale. That's the second way to be able to tell whether we have increasing returns to scale or decreasing or constant returns to scale. The third way is particular to the Cobb-Douglas approach. Generally, a Cobb-Douglas production function is usually, as we've seen, a function of capital and labor. So let's say in this situation, the capital has a power of alpha multiplied by the labor, which is power of beta. So irrespective of whatever the coefficient is, it doesn't matter. Capital has a particular power and labor has a particular power. So if we are to have increasing returns to scale, alpha plus beta must be greater than 1. So when we add them up, they must give us a value that is greater than 1. If it is decreasing returns to scale, alpha plus beta will be less than 1. And if we have constant returns to scale, alpha plus beta will be equal to 1. So let's go to this production function that we have here, which is this. Here we can say that the alpha in this instance, which is the power of capital, is 0.5, and the beta, which is the power of labor, is 0.25. So alpha plus beta, which is 0.5 plus 0.25, that will give us 0.75. This value here is less than 1. So that means the firm is experiencing decreasing returns to scale in the long run. And this is how we can tell if the firm is experiencing increasing returns to scale or decreasing returns to scale or constant returns to scale. And this solves the last question. Thank you very much for watching. If you did enjoy this video, please leave it a like and do not forget to subscribe to the channel. Thank you very much. See you in another video.